Chapter 13 is all about solutions. The general definition of a solution is a homogeneous mixture of more than one substance. In a solution, so before we get started on that, oftentimes I think of a solution as like putting salt in water, right? So dissolving something. But technically, it just has to be a homogeneous mixture. So that could be gas in a gas, a liquid mixed in a liquid, a solid dissolved in a liquid. It could be all of the above, but it is a more general definition. So the solute is uniformly dispersed throughout the solvent. Solutes are what makes up the majority, where solvents are what makes up the minority. And we talked about that in a previous chapter. So again, solute, minority, so something that has the smallest amount, versus solvent is the majority. So whether or not a solution is going to happen will depend on a few things. First thing, the natural tendency towards mixing. So one of the reasons why I wanted to talk about thermodynamics before we did this chapter is to talk about entropy. So mixing generally, especially with gases, is a spontaneous process. If I have two different gases and they're separated by a barrier, once I open that barrier, they're more likely to be mixed throughout. So this mixing increases the amount of randomness, which therefore increases entropy. So when we form solutions, this is a favored process by the increase in entropy that happens when we have that mixture. Another thing that will affect whether a solution is created or not is intermolecular forces. So that could be dispersion with other dispersion molecules, so two nonpolar things interacting via dispersion forces, two polar things interacted via dipole-dipole, something with two things with hydrogen bonds, and then ion dipole, which we're going to really dig into. But any intermolecular forces can lead to the mixing between solute and solvent molecules. So to form a solution, we have to take our solute, which in this case is sodium chloride, and we have to take our solvent, in this case it's water, and we need to break our solute apart. So we need to break any solute-solute interactions. They need to be overcome. So this is an endothermic process because we have to add energy in to break up those attractions. We also need to take our solvent, and they're hanging out via their own intermolecular forces, and we need to break the solvent-solvent attraction. And so we need to overcome that as well. We don't normally think about that, but technically these molecules are next to each other and we need to make room for the solute to fit in there. So this is also an endothermic process. Then we have an attraction between the solvent and the solute molecules or particles. So that is an attraction, so that would be an exothermic process. So whether a process is going to happen or not will depend on the magnitude of these processes. So if my endothermic solute-solute and solute-solvent is small enough and my solute-solvent interaction is large enough in the exothermic direction, my solution may or may not form. So it really gets back to delta G. So Gibbs energy, right, is equal to delta H minus T delta S. We know that when we go from having let's say solute plus solvent on their own to creating a solution when they mix together, that is an increase in entropy every time because we're mixing. But for our enthalpy of reaction, these are endothermic processes breaking up these solute and solvent interactions, and then creating our solution is exothermic. So depending on if we have these that are more endothermic, then our solution process is exothermic, then this value would be positive. Where if our solution releases, when we create our solution, it releases a lot more energy than it takes to break apart our individual components, then this part would be negative. And so basically it's all thermodynamics. So let's look at these questions and kind of determine whether there's going to be good mixing here. Which solvent would be best? And so in general, the key term is like dissolves like. So things that are polar are going to dissolve well in solvents that are polar. Non-polar would prefer to dissolve in things that are nonpolar due to their interactions. So I have a hydrocarbon. Hydrocarbons tend to be nonpolar. Here I have sodium sulfate. That is an ionic compound, so by definition, very polar. Hydrochloric acid is a polar molecule, and iodine is nonpolar because it's just two ions interacting. So, would one of them dissolve in carbon tetrachloride? Now, carbon tetrachloride looks like this. It is tetrahedral with 4 identical chlorine atoms around it, no lone pairs, a non-polar molecule, and water, as we know, quite polar. So, the polar molecules, like the ionic compound and the polar hydrochloric acid, will dissolve really well in water. And our non-polar molecules here, those are going to do better in carbon tetrachloride. So which of the following solvents will best dissolve wax, which is a complex mixture of compounds that are this long chain of hydrocarbons? So we're going to want something that has a similar structure. So right away I know acetone and water are polar, so those are not going to work out. But hexane, benzene, and carbon tetrachloride are all nonpolar. So we want to find the one that's going to best dissolve wax is going to be one that has a similar structure. So I'm going to get rid of a small carbon tetrachloride, and then also benzene, because the hexane here has that structure of 6 carbon chains in a row, so that matches the best with the wax structure. So hexane. Back to the energy stuff, your fave. So I like this image because I think it really describes what's going on here. So to break up the solvent molecules, we call that delta H solvent. That's endothermic. That basically, to make room to break those particles apart, to make room for the solute. Then we have our solute molecules or particles, and we have to add energy in to break those apart. So this line here is adding both of those processes together. That's our total, kind of like our reactants. And to create our solution is this red line. That's the mixing. So we have the same thing here. Here we're endothermic, total of our solute and solvent. And if our interaction between our solute and solvent molecules is large enough, really strong attraction, then our mixing here is going to be really large. And so if that's the case, then our delta H is going to be exothermic for this solution process. If they don't have as strong of an attraction, then our mixing enthalpy is not super large, then our process will be endothermic. So to make a solution, again, we need to break apart all of our solutes. So the delta H solute is endothermic. And then we also have to break apart our solvent molecules. That is also endothermic because we're breaking some bonds. Then we're going to form our new attractions for mixing. That is exothermic. So in general, we need to check out the relative sizes of the delta H for each of these processes to find out the solution enthalpy. So this is where our Gibbs comes in later. So we're going to take our solute, solvent, and mixing and add them together, keeping in mind this is always positive, and this is always a negative value. So if we end up getting an endothermic reaction, so our solution here ends up being this top case, then if we have our Gibbs energy, right, delta G equals delta H minus T delta S. So if our enthalpy of solution is positive, to get this process to happen spontaneously, I need my entropy to really matter. And so the temperature is also going to come into effect. If it's an exothermic process where delta H is negative, then these processes are always spontaneous because we have only favorable enthalpy and entropies. When we create a solution, the solution process is one direction, and going the opposite way and reforming our solute and solvent that are separate is called crystallization. When we have reached a point where these processes are equal, the rate that they're happening is equal, then we're not going to be able to get any more solute to dissolve. This is called a saturated solution. So this means you could add any more solute or solvent in there and you're not going to create any more solution. You're at capacity. So if we haven't reached that yet, so if I could add more solute and get it to dissolve and mix, then that solution is called unsaturated. So the only way to know that we have reached capacity is if I have a solvent and I add a bunch of solute to it and it's dissolving, and then all of a sudden it stops dissolving. And I do get a bunch at the bottom. Okay, then the solution I have above here, that's my saturated solution. Solubility is related to this. So solubility of a certain compound is the maximum amount of solute that you can dissolve into a solvent at any given temperature. So temperature is important to this, and we're going to talk about that soon. So saturated solutions are at their solubility, so they have reached solubility of that solute in the solvent, and unsaturated solutions have less than that amount. And then there's one more, which we'll get to now. So supersaturated solutions are when our solvent has more solute than it should at that temperature. So these are very unstable. And crystallization can happen by bumping it, adding a little speck, a little crystal, scratching the surface, really any kind of minor stimulation. So here's a supersaturated solution. You can't tell by looking at it, but if you add a little crystal here, then it will start to crystallize out, and then all of the extra solute that's in there that shouldn't be will crystallize out. These are really uncommon. You kind of have to intentionally do those, and we'll talk about how to make them in a minute. So factors that affect the solubility of a solution, one is just that solute-solvent interaction. So like I said, like dissolves like. So the stronger those interactions, so the more similar the intermolecular forces are, the greater the solubility. So basically, more exothermic that's going to be, we're going to have a large delta H of mixing. So even things that are not very polar can still dissolve in water. So gases, these nonpolar gases, nitrogen, oxygen, argon, and krypton, because of their their LDFs, they're able to dissolve in water. So you can see as their LDFs increase with molar mass, their solubility also increases. So increase of mass, molar mass equals increase of LDFs, which equals increase of solubility. The next one is liquid-liquid solubility. So this is specifically a type of solution where we say that liquids that mix together are called miscible, and liquids that do not mix together are called immiscible. So one of the common ones you might be familiar with is salad dressing. Oil and vinegar, two liquids. They don't mix together very well. They are immiscible. Where if you have something like alcohol, for example, if you looked at like a bottle of wine, you would see that there's ethanol and water both in there, and they are mixed together equally. They don't separate, so they are miscible. So hexane and water are polar. Another example would be like acetone. Though acetone that if you buy it over the counter, that's a low percentage of acetone and it's in water. So those are miscible. Another type of thing to think about are organic molecules. So these can dissolve in water, specifically if they're polar. So organic molecules tend to have carbons and hydrogens, and those are very nonpolar, those bonds. And so when we are able to add the oxygens and hydroxyl groups, then it helps to increase the solubility. So polar organic molecules dissolve way better than nonpolar organic molecules. So here I have cyclohexane, all carbons and hydrogens, very nonpolar. If I add some hydroxyl groups here, these are OH groups to the carbons. So it's very similar structure, but now those oxygens on there make it nonpolar due to their lone pairs. And so this molecule can do hydrogen bonding, and so it's much more soluble. This is glucose, right? It's very soluble in water. In biological processes, vitamins that we take, these are dissolved into different parts of our body. So fat-soluble vitamins, like vitamin A here, notice it's a very nonpolar molecule, and so when we ingest them, they are stored in our fatty tissues because our fatty tissues are nonpolar, and so this is where it's stored. So you don't have to take vitamin A every day because it's stored in there. But water-soluble vitamins like vitamin C, notice a lot of OH groups, so very polar. And so it will stay with your blood and in your urine, and you need to take those daily because they're basically being excreted very regularly. Some other factors that affect solubility are pressure effects. So this is specifically important for gases. Solids and liquids are not really affected by pressure because they're incompressible. Incompressible. Where gases, you're able to apply a pressure, force them into the solution and to interact with the solution. So here we saw this with vapor pressure, right? Now this is important if I have another type of gas that's not made up of my liquid. If I apply a higher pressure to that solution, I'm going to force more of the gas molecules to interact with my liquid, and then they'll regain that dynamic equilibrium, and basically I end up with more gas molecules in the liquid. So the solubility, which is equal to the concentration, okay, keep in mind it's a concentration value of gas. So the solubility of the gas in the solvent is equal to the Henry's law constant, so it's for every gas in a certain solvent, times the pressure that's applied of the gas up top. So this would be the pressure that you apply of the gas molecule. So you can see as I increase the pressure that you apply, the solubility goes up linearly. So this is really important for like carbonated water. So at my house, we make carbonated water. And we apply a bunch of carbon dioxide gas into the water and shake it up, and it helps to force the CO2 to dissolve in the water, and then when we're ready to drink it, the bubbles can start to come out. So let's use Henry's law to calculate the concentration of carbon dioxide in a soft drink bottled with partial pressure of CO2. So this is pressure of CO2 equals 4 atmospheres over a liquid at 25 degrees Celsius. Henry's law constant for this at that temperature, so KH equals 3.4 times 10 to the negative 2 molar per atmosphere. So we'll use our equation, solubility of gas, in this case CO2 equals Henry's law constant times the pressure of CO2. So that will be 4 atmospheres times 3.4 times 10 to the negative 2 molar per atmosphere. Notice atmospheres will cancel out, and I get a concentration of 0.136 molar of CO2. So after you open the bottle and the solution has, the CO2 has been able to equilibrate, and now the partial pressure on top of the can of soft drink is way lower, 3 times 10 to the negative 4 atmospheres. What's the concentration? So we'll do again, solubility of gas equals KH. We're at the same temperature, so it'll be the exact same number. So I'll have 3.4 times 10 to the negative 2 molar per atmosphere times the pressure. It's way lower, 3 times 10 to the negative 4 molar. So then we'll multiply those together, and I get 1.02 times 10 to the negative 5th molar. Nope, this should be atmospheres. My bad, atmospheres. So notice my concentration dropped in the solution a lot more. That's why if you have a can of soda, you open it after a while, it'll go flat because all the carbon dioxide has been able to escape because you're not applying a pressure to it. Okay, the next thing is temperature effects. So in general, if I want to dissolve more solid into my like my coffee in the morning, let's say I want to dissolve more sugar, then I'm going to increase the temperature. So in general, for most solids, as the temperature increases, so does the solubility. In some random weird cases, and honestly I don't know why, it either stays constant or it can decrease. So for cesium sulfate, it can decrease. For all gases, as temperature goes up, solubility decreases every time. So, and this is like common experience for us, right? If I open my can of soda and I want to keep the carbonation in there, I want it to stay bubbly, will I either put it in my fridge and keep it cool, or will I put it out in the hot sun? Well, from my experience, putting it in the hot sun makes it go flat really quick. Where keeping it in the fridge, I might be able to make that last a little bit longer. So that's basically the trend here. And another example is cold rivers tend to have higher oxygen content than warm rivers, which is, good for fish. So we have talked about solubility and just generally solutions very qualitatively, whether they're saturated, unsaturated, supersaturated, but we're going to talk about specific amounts now, and this is going to be really important as we talk about calculations. So the types of concentrations I'm going to mention are going to be mass percent, parts per million, and parts per billion, and these are all very similar. There's mole fraction, which again is actually very similar, and then molarity, which we've learned about, and then molality. So you really just have to learn like one kind that's way different, and well, they're all actually really similar. So, and then one thing I want to talk about is how to make a solution, which maybe you've done in lab. Once you know the amount of solvent and solute you want to make, well, once you know the amount of solute that you need to put in and the total volume of solution, what you'll do is you'll weigh out your amount in grams of your solute. You'll then pour it into a volumetric flask. Then you'll fill it up about halfway with water and mix it. And then, well, I'm going to go against this graph. So fill it up about halfway, mix it up, make it all dissolve. And then you'll fill it up to the line. Volumetric flasks are really nice because they have a graduated line right here on their narrow tubing. So you're able to easily get exactly the volume you need. So you'll do that, and then you can invert it a little bit and get it dissolved. So in class, I want to work on calculating concentration. I'm going to teach you each one in this, but we're going to practice in class. So feel free to try some of these exercises on your own, but we'll work on them in class. But in the upcoming slides, I'm really just going to go over the equation. So for mass percent, it is exactly what it is. It's the mass of a component, in general it's a solute, over the total solution. So we're going to take mass, if I want to know mass percent of NaCl in my solution, I'm going to take my mass of NaCl over my mass of solution. Oops. Now keep in mind, that's going to be mass of solute plus solvent, so NaCl plus water. And then I'm going to times by 100. So percent means per 100, so that's why we have to multiply by 100. And that's going to make the next ones really helpful. So again, mass of your component over the total times 100. For parts per million and billion, very similar, actually exactly the same as percent mass, but you're going to do mass of your component divided by total mass. For parts per million, you're going to multiply by 1,000,000. For parts per billion, you're going to multiply by 1,000,000,000, or 10 to the 9. So same kind of thing, but this is really important for really dilute solutions, and this is, you might see this commonly reported in air quality for different types of hazardous or toxic chemicals or particles, since gases are so much more dilute, but it still can be harmful to us in these low amounts. So again, it's going to be the mass of your component, so if this is mass of A, over mass of total, which will be A plus B, which is solute plus solvent, times we'll do 10 to the 6 for parts per million, and then mass of A over mass of A plus B plus C if there's more, times 1,000,000,000 for parts per billion. In mole fraction, again, it's actually very similar. It's the fraction of the moles instead of the percent of the mass. So we're going to do, mole fraction is going to be the moles of your component, let's call it A, over your total moles. So we'll do moles of A plus moles of B. Now we're not going to multiply by 100, so your minimum value is 0 if you don't have any, and then you can go all the way up to a total value of 1 if you don't have a solution and it's just pure components. And then if I want to know how much I have of the other thing, I just can subtract by 1 or solve for it. And these do not have units, so you'll just, when you do it, you'll do this equals, the mole fraction is this chi value of A. So make sure you label it. So if I want to know for this one, the mole fraction of HCl, I want to write chi of HCl equals, and then and I'll write my answer. The last one we're going to talk about is molarity and molality. Now we already learned about molarity in one of our previous chapters in General Chemistry 1. As a refresher, molarity is going to be big M, and this is moles of solute over total liters of your solution. So it's important that we really be careful about how we write. If you're one who likes to write capitals all the time, or you like to write lowercase all the time, like no longer, you must be distinct in this, because molality is a very similar word but also similar notation. It's little m now, and it's moles of solute, so same numerator, but now kilograms of the solvent, so not over the solution. So moles per kilogram. Now if we happen to be using water as our solvent, and this is a very dilute solution, then our molarity and our molality will be very similar, because 1 gram or 1 kilogram of water is equal to 1 liter. So if it's a dilute solution where where I don't have very much solute and most of my mass and most of my volume comes from the solvent, then this is going to be the case. One thing that's kind of nice about molality is it doesn't change with temperature. So mass is a mass, right? Mass at 25 degrees Celsius is mass at 100 degrees Celsius, where molarity is going to vary with temperature because the volume can change. If I heat things up, they tend to expand, and so volume will increase. So when we are going to be doing boiling point and freezing point calculations later and seeing how that will change with temperature, we're going to be using molality because it's going to be a constant value and it won't be different at different temperatures. But we can also convert between molality and molarity by using the density of the solution. Because I can get density is grams of your solution divided by liters of your solution. So if you know how many moles of solute you have, then you know you can find how many kilograms of solvent based on your grams of solution. So we'll practice that in a little bit, but you do need the density to convert between the two. And reminder, we are going to practice the practice problems in class, so be ready to learn.